Thank you so much. You forgot one of my most important roles, which is mother to four, one of whom is sitting right here. So, hey, hi there. Hopeless people, hopeless. She has heard it all and then some, between my husband and I. Okay, so thank you. It's a great, great honor to be here, and it's been so fun to meet the next generation of scientists. It's so inspiring. People who are going to change the world, change science, change our institutions of science. I am so moved by your enthusiasm, your insights, and your optimism. So thank you for that. Thank you for this gift of sharing that with you. And today I'm going to talk more about the technical aspects of my coral research. But I hope that the talk yesterday is something that is recorded that people might be able to see, or I can definitely send my slides around. It's a whole different thing. Went to a very different place. And it's kind of worth reflecting on our roles as climate scientists. And I'm not going to get into that today, but definitely let me know if you're interested in those slides. I can send them to you about this era for climate science, what we're facing as scientists and humans, frankly. But today we're talking about El Nino in the mean state in the tropical Pacific, and what we know and don't know, and what we can learn from 20 years of working at these sites in the middle of nowhere to try to amass some more data from this data sparse region. And this is my student, Pam, looking like a kid in a candy store, sitting atop of a huge pile of fossil corals that she used for her PhD to reconstruct El Nino and tropical Pacific mean state. And these are other portions of my coral side of the lab here who've been instrumental in generating these records over 15 years at Georgia Tech. And these are some really important collaborators that have been long involved with the project, from Scripps and University of Minnesota, Minneapolis, and Sam Stevenson, who's now at UCSB, a very long-term collaborator as well, and I know a former staff here at NCAR. And so we're going to talk about El Nino today, and I'm going to start with the confluence of El Nino and the corals, which is illustrated here in a paper by Terry Hughes, noting the devastating impacts of the 2015-2016 El Nino event on some corals across the tropical Pacific and Indian Oceans, most notably, where we saw really 30 to 90% coral bleaching, coral mortality at many, many different sites. And of course, not all of this was caused by the presence of an El Nino event, but a good portion of it was in combination with the baseline warming that has been underway here for 50 plus years in earnest. And of course, turning to the cold side, we also have big considerations for the cool phase and its impact on global climate patterns. Of course, this is a iconic picture from the 2017 hurricane season in the North Atlantic. Of course, North Atlantic hurricanes are one of the many kinds of climate extremes that are impacted by the state of the tropical Pacific sea surface temperatures. And of course, we're heading into uncharted territory, just getting our way through the spring predictability barrier here, looking at a prognosis for possible weak El Nino conditions by the end of the calendar year. I think we can all kind of, squint our eyes and realize that we really can't say very much right now. It's early, but that these kinds of predictions are really important in enabling communities across the world to prepare for the extremes and what they bring to human and ecological systems across the world. And so these are some of the kind of questions that we turn over in the long-term ENSO community. So these are people who are really interested in how El Nino evolves. ENSO evolves over decadal to centennial and maybe even millennial timescales, trying to understand if we can use past records to query the sensitivity of this natural climate cycle to external forcing, which is kind of the ground zero for understanding its near-term evolution under greenhouse forcing. So we can turn to volcanic eruptions, solar variability, precessional forcing, and of course we can pretend to query the greenhouse forcing itself if we have long enough baseline in the pre-industrial, which is what we're going to talk about today. So these are some of the playgrounds for paleoclimate scientists and modern climate dynamicists to try to pick at this question with a key purpose in mind. And so we can also think about the relationship not between forcing and response, but with respect to internal variability and the degree to which changes in the mean state of the tropical Pacific, or generally speaking, the tropical basin, the Pacific basin in general, may impact the properties of ENSO itself. So we may think about looking at this over the 20th century and how the 20th century changes in mean state have determined ENSO properties or not. We can think about playing this game over the last 2,000 years, where we have reasonable records and maybe a prayer of doing this with constraints on the mean state and constraints on ENSO properties. We can look at beyond that time frame over the Holocene, where we get even much fewer constraints on the mean state and ENSO, and then of course dim views into the LGM as well. And so you can play this game with data, you can play it with models, and you can play it in integrated data model sense, which is where we're going to end up by the end of this talk. And then we can ask this third question here, which is kind of the null hypothesis hanging around our necks, which is, are we really kidding ourselves? Is there really any deterministic properties of the long-term expression of ENSO? Or is this all really a sick joke? And so this is kind of crushing us with respect to the bar for actually detecting any forced response in this system, or really concrete relationships between the mean state and ENSO properties. It just kind of walks around and it does a lot of stuff, and it's really hard to tell what's going on. So this is going to foreshadow the need for an awful lot of data if we're going to bring anything to bear from the data perspective into this, into any of these first two categories of responses. And so what we're going to talk about today are a suite of islands in the Central Pacific. These are the Northern Line Islands, and so we have 3 islands that we've been working at for 15 years. So we have Palmyra, Fanning, and Christmas. Christmas is the place where we've done the most work, and I'm going to show you the most data from that. It's at 2 north wind, 57 west, so it's very heavily impacted by El Nino properties. We'll talk about that in a minute. But these are archives that are extracted from underwater, living coral archives that cover the last decades to century or so. We're going to talk about our calibration interval in a minute. But these are growing 1 to 2 centimeters per year. And so these afford sub-monthly resolution of the ocean temperature reconstructions that we're going to be talking about today. And if we want to move beyond the 20th century, if you will, we have to turn to these so-called fossil coral archives, which are corals that have been lying around in the beach for decades to centuries, in some cases millennia. And the oldest corals in this class from these particular islands go back 7,000 years. But many other people have been working through archives across the tropical Pacific that go back several glacial cycles. And so this is a game you can play over many different timescales. It's just that at these sites, we're going to be looking at the mid to late Holocene as a data interval that we can add a lot of data to. And these are corals that we have to use uranium-thorium dating to figure out when they grew, because of course, they all look the same to me. So a 50-year-old coral, like one of these on the beach, looks exactly the same as a 7,000-year-old coral. And it's really annoying, because it means you have to bring back everything to the lab, right? And then you date it, and then you figure out what you'd like to work on and run through the mass spectrometer, which is, a tall order. It's a very high-end kind of proposition. That's why it's taken me 15 years to get here. So how do we reconstruct ocean temperature with this coral archive? And so here you can see a cross-section of the coral, and you can count back in years. We're measuring the oxygen isotopic composition of the coral, which is kind of shorthand there, the delta notation. And the coral oxygen isotopes are a function of sea surface temperature and the oxygen isotopic composition of the seawater in which the coral grew. And so this has been shown empirically again and again and again. And so depending on the relative contributions of sea surface temperature and delta 18 of seawater at your site, you can have a variety of different expressions of climate dynamics written into your records, right? Depending on whether you're salinity-driven or temperature-driven or both. And so this proxy right here on the seawater delta 18 side is really something that is driven by large-scale P minus E, basically combined with ocean circulation. And so this is more or less a salinity proxy. It's driven by the same things that salinity is driven by. It's not perfectly a salinity proxy because there are some isotopic effects that occur on phase change that make this have some other degrees of freedom than salinity. But 90% of the variance is explained by salinity. And these are a whole slew of papers that have been really looking into the relationship between delta 18 of seawater and salinity. And I point in notably to my own postdoc's work, Jess Conroy, who's really done a lot of work in basically pinning down some observations. We're going to come back to that a little later in the talk. So this is a combined proxy, as many of you may already know. And so how this plays out in the Northern Line Islands is fairly straightforward, at least for ENSO, for which we have some great ground truthing in terms of what the temperature variability is and what the salinity variability is. We don't have this kind of plots over decadal timescales. We certainly don't have these kind of plots over centennial or climate change timescales. So what I'm going to show you is really a framework that is best applied to hunting El Niños in this kind of archive, and is why this proxy is a good fit for that purpose. So on the top here, we're plotting sea surface temperatures for February 2016. Obviously, it gets warm during El Niño conditions at the site. And in the bottom here, you can see it gets wet. This is OLR at the site as you track that shift in convection during large or moderate El Niño events. And so this plays out very favorably in terms of coral oxygen isotopes, because we have the coral oxygen isotopes being driven down. It's a lower coral delta-18 values during warm conditions. That's a thermodynamic effect that has been well established for 70 plus years. And then the bottom here, we have the fact that when it gets rainy, you change the surface oxygen isotopic composition, also decrease it, push it down, which gets incorporated into the coral skeleton. And so that's rainy conditions drive it also down. And so during El Niño events, we have this compound signal at play in our records, driving a larger signal-to-noise ratio in our material with respect to other sites that could be used across the tropics for ENSO reconstruction. This is just a really good proxy for the specific purpose that we're interested in today, which is the reconstruction of ENSO in tropical Pacific mean state. So this is the calibration. I showed this yesterday during my talk. And so this is 8 different corals in different colors, all of them at monthly resolution, which is the standard resolution that we collapse our data down to, from about 15 to 22 points a year down to about 12 points a year. So they're really highly resolved kind of records. And they're really well replicated over this particular calibration interval. And you can see OISST in gray. If you squint hard, you can hardly see it because it's really overlain by the corals themselves, which are well replicated across the cohort, the ensemble. And so, further up on this plot is towards warmer El Niño conditions, and further down on this plot is towards cooler La Niña conditions. And these are really the result of years of piling on different kinds of records onto this plot from different kinds of students' work, going back to Mike Evans' work in 1999, who generated the first record from this entire region as part of his PhD. And so on these kind of timescales, we know enough about the magnitude of sea surface temperature variability on interannual timescales, and let's say salinity variability or delta-18 variability in seawater over these timescales, to know that the sea surface temperature is contributing at Christmas Island roughly 80 to 90% of the variability that we see in the delta-18 of coral. So that's a number to keep in mind for later when we start to talk about the signals that are emerging from looking at the pre-industrial data to today. So if we look at the interannual variability we've been able to amass to date, we have a plot that looks like this. And we're going to go over this in quite a bit of detail. And I showed this yesterday, and we're going to really take it to the next several steps of analysis and thought in terms of understanding what it means for our climate future. But on the x-axis here, we have time, where it's going backwards. So here's 7,000 years ago, and we're running up to 0 years before present. And then on the far right is the different islands representation of El Niño variability, and from the 20th century records and the variance that's contained in those records. And so on the y-axis here, we have the relative change in ENSO strength, if you will. This is a standard deviation of ENSO, which is really the standard deviation of a 2 to 7 or 2 to 8 year band-passed records in kind of sliding windows. And so you take your coral record and you band-pass it, and then you can slide this window across, and you can get a representation of the degree of variability of ENSO across the records. So we have some lower variance portions of individual records and some higher variance portions of those records. And those are the spread of error bar from maximum variance realized in that record to the lowest variance realized in that record. And most of these records are a range in age, in length from 30 years to 300 years. So that big dot is 300 years. That's the big dot on the plot. And some of these tiny, tiny ones that aren't even filled in are less than 20 years. And so we kind of want to downweight those visually for you. And so this 0 line here is defining the standard deviation of ENSO in the 87 to 2007 period, which is an arbitrary benchmark, but it's the one that we use to measure relative changes about. And so if you're higher than this line, it means that there's a portion of your record that has a variance that's higher than the specific benchmark. And if you're lower than this line, it means that you have portions of your record which are lower variance than that particular benchmark. And this is in percent units over here. So just stepping through, you see the 20th century records contain appreciable degree of spread of ENSO properties, right? We have intervals that are pretty high in variance, and we have intervals like the mid-20th century, which are relatively low in variance. And so that's really reflected in the total error bars. The gray swath here is kind of the range of 20th century realizations of ENSO properties in 20-year windows. And so here's all the fossil coral data from the different islands. And so they're benchmarked against their modern coral, same benchmark for the different islands. And they're all benchmarked kind of in an apples-to-apples comparison. So Palmyra to Palmyra, Fanny to Fanny, and Christmas to Christmas. And in general, you can see that most of these data sets in the fossil coral realm are falling below this kind of late 20th century benchmark that we have defined in this record. And so not all of the data that I've generated is falling below this red line, right? So there's some little segments of 20 years here that in these records in particular, which are indicating 20-year epochs that are higher in variance than the late 20th century benchmark that we have chosen. So that's how you would interpret that. So it's not unprecedented, this level of variability. But that's a lot of data over here. There's over 2,050 cumulative years of fossil coral ENSO reconstructions on this plot, okay, outside the 20th century. So that's covering 7,000 years, not in its entirety, but we've amassed a lot of data in this plot. And so obviously the question becomes, can we bring some way to assess the changes in the pre-industrial era relative to an epoch like the late 20th century? How can we begin to bring a significance test that reflects the fact that this is a highly variable system, the current levels are not unprecedented, but there's a lot of data here, right? We need to design something fit to purpose that's quite sophisticated in its application. And this is what we're going to do. I'm going to step you through this, and then I'd love to hear your feedback and thoughts on this. It's definitely not a done deal. I feel it's the best we can do right now. So we're going to form a null hypothesis, which basically states that the observed distribution of samples that we saw in my whole reconstruction is just the result of chance subsampling of a highly variable but stationary system. Okay? So that's the null hypothesis that we're going to frame our analysis around. And so in order to pull some samples from this kind of null, we need to have multi-millennium stationary realizations of ENSO properties. And then we're going to sample those in a kind of Monte Carlo framework in order to see what kinds of observed distributions of variance we can get in different segments of data from these nulls. And so, of course, we don't have anything like this in the real world, right? So we really are going to have to turn to, obviously, some kind of model output to try to represent a stationary null that is appropriate for our testing. And then we're going to subsample this with a lot of little pseudo-corals that we've cut from these long simulations, and we're going to pilot statistics around what kinds of changes in variance are possible. Do they match the observed change from pre-industrial to today? All right, and then we're going to look at the distributions relative to the observed.
Can you say quickly what you mean by ENSO variance? Is that bandpass in some way?
Yeah, so we do a couple different metrics. I'm happy to send you the preprint, but we do, well, we've done several things. So we have the first pass was a 2 to 7 year bandpass filter. So we've done 2 to 7, we've done 2 to 8. They seem to yield the same conclusion. And then what Pam has done more recently is different. She has taken, I have to, she has taken a 13-month boxcar average across all of the data. And then she has taken the standard deviation of 10-year high-passed version of that time series and compared how those two metrics of ENSO strength look at in our analyses, in our plots, and things like that. So there's only two we have tried, and they're very different. And one is better suited towards longer time series. One is better suited towards shorter time series, but we've tried to allow our analyses to unfold on both of those, using both those metrics. Maybe we can talk about that in Q&A if you have thoughts. I'll give you some time to come up with some thoughts on that. For now, let's jump to our long stationary nulls, okay? These may not be perfect, but they are the best we have. Betty's sitting there nodding, so. So what we're going to apply here is obviously, one is a statistical model output from the linear inverse model of ENSO generated, really tuned over the last 50 years of instrumental data that are obviously pretty good at constraining the relationships in the system and time space. And this is really the work of Antonietta Capotondi. She allowed us to get this data set pretty early and start crunching on that. And I'm going to show you an example of that output in a second. And the other one, I'm assuming a lot of people here are pretty familiar with, the LME, the Last Millennium Ensemble, playing with these really incredible sets of, and that should be 10 times 10,000, 10 times 1,000 years, not 10. Thank you. A little typo. So these are really an incredible trove of additional kinds of null, a dynamical null in this case, from output from the NCAR model. And so this is output from the LIM. I just wanted to give people a sense of what this looks like in time series space, because we rarely look at it in that space. So this is the observed Nino 3.4 time series. We all know that probably pretty well. And then this is an example randomly cut from the LIM Nino 3.4 index as is plotted here. And if you look at it by eye, it has some similarities. It's a little bit punchier, I would say, than the observed. And I think that really is because it's tuned on this kind of punchy interval in the instrumental record, which is 1950 to 2000. So that's where we have some of these larger events, some of these more consistent spacing. And so it's good to keep that in mind, that this is a characteristic of this null, that it is a little bit, on average, higher variance than some of the lower variance intervals of the So I think it's really important to remember that this would just be, in a statistical sense, one realization of a statistical system that can spit out a lot of different walks through this space. And so that's just important to realize. I could have cut another period. In fact, let me go to the next slide, where we can look at an interval of 5,000 years. This is from Matt Newman, my colleague Andy Newman. He's a geophysicist in Georgia Tech. Very different. So this is 5,000 years of Matt Newman's output for similar flavor limb, just the one I had available last night. But what we're looking at here is the sliding variance, basically, Clara, through this Nino 3.4 time series. And so we can take the variance in these windows and slide it through. And here you can see that you can really achieve some very kind of sustained high variance intervals in this limb output. And you can also achieve some very sustained low variance intervals and kind of everything in between. And so the late 20th century would be one fairly random realization of this PDF, right? So that shouldn't be surprising, and it doesn't mean that this limb is right or it's wrong. It just means that it's a defensible realization of our system, which is grossly poorly constrained. So that's the issue. So yeah, I'm flagging for you those kind of high variability centuries where you get parked in this high variance state and it's kind of more punchy, and then you can get parked in these very low variance states. So this is a really, I want to flag for the early career scientists in the room how powerful these kinds of tools are in generating thousands and thousands and thousands of years to dig into some of the statistics that we just can't get at very easily, even with dynamical models right now, the cost that it takes to run them. And they have their strengths and weaknesses, but they certainly have their place in studies like this when we need these really long stationary realizations. So what do we do when we stack up the statistics of these pseudochoral ensembles from these stationary knolls against what we actually see? And so what we've done here is I'm comparing a test that takes all of the pre-industrial fossil coral data and takes the last 50 years of our coral data, which is the last interval for which we have all 3 islands at play. And we see that there's an observed change of 30% going from all pre-industrial, the mean across all the pre-industrial data, to the mean of the last 50 years. So it's a 30% shift across that set. And if we use those knolls to recreate ensembles that have the same number and length of sequences as our actual, right, as our actual coral data set, and we stack them up against these knolls, here's the limb knoll. You can see that we can get 30% changes sometimes, but very, very rarely with that particular knoll. Okay? If you go towards the LME, you see it's a bit more forgiving. You can get larger changes in statistics here, and so you would have to go out to 40% to get that change in 99%. And so our observed change at 30% is falling above the 95 for the LME null, but not above the 99 for the LME null. And these are just reflecting different possible ENSO realities out there. It doesn't make either one of them right. It doesn't mean that our change is not consistent with chance sampling of a stationary system. It just means that for the best nulls we can bring to bear, we get this conclusion, that it is significant above the 95% level, that there's been a change, that this is not consistent with stationarity in the system. So it's not just this study, though. I really want to emphasize that it's been a heady 5 years for paleo-ENSO work. People who are trying to answer this question in a variety of different proxies in a variety of different settings. And so here's the coral work that we've been undertaking. I first kind of put this out there in 2013 with a hell of a lot less data, frankly, and really probably poor nulls. Now we have better nulls and a lot more data, and so that's my student Pam's work under review right now. And I was also involved with this study, which I wanted to flag because it's truly exceptional in the amount of data that they brought to bear, 740 years of continuous tree ring delta 18 from Taiwan that has a very robust and statistically significant correlation with Nino 4 in that case from Taiwan. And this is like, 15 individual trees analyzed for isotopes and replicated across this ensemble. It is an insane amount of data that they brought. And I helped them with statistical testing for this change in ENSO properties from the pre-industrial to today. And so, of course, you may know Shane McGregor's work is a little bit older. In Lee et al., the Java tree rings, finding the same thing. So the idea emerging from this set of literature is that there may already be a detectable change in ENSO properties coming into the recent decades relative to a long baseline of pre-industrial conditions. The kind of thing you could only pull out when you have this much data on the table. Right? We could wait 100 years to pull this out of instrumental data if we're lucky, right? This is something that is, I think, a compelling target and something we should think about. And so we can think about whether this implies a role for greenhouse gases or not. This is obviously a statistical finding. It's not a dynamical finding, but let's dig into that a little bit more. So what I hope I've convinced you is that there are a variety of paleo records of ENSO that seem to imply that there's been a change in ENSO properties. But it's important to realize that none of these are purely SST proxies, right? They're all reflecting some component of hydrological response to ENSO conditions. That includes my own coral record. I mentioned it's at least maybe 10, 20% salinity driven. And that's certainly true for the Taiwanese auction isotope records, right? That's almost a purely hydrological signal in that case. So all these proxies are blended temperature and hydrological impacts. So we can actually frame a new and more salient question, which is the underlying variance of this phenomenon actually already increasing? Is that what these records are collectively telling us? Or are we already seeing some of the emergent properties from the model simulations of greenhouse gas implications for ENSO falling out in these records, which might be glibly referred to as more rainfall bang for the SST buck, we predict should be emergent from the supposition of changes in the mean state in the tropical Pacific with even an average El Nino that's unchanged in the future will have a greater hydrological impact in a greenhouse world. And so this is just showing you in maps that are very difficult to read here. Sorry about that. Like yellow turned into clear. Okay, at any rate, I think you can still see what I'm trying to point out, though, which is that this is from Chai et al., 2015. You're probably already familiar with this, but just in case you're not, these are CMEP5 compilations of what happens to hydrological responses to El Nino conditions in control simulations and in climate change scenarios. And the difference here with the stippling, faint as it is really indicating that there is a larger hydrological response to your average El Nino event in a greenhouse world. And that's something that has been borne out in model conditions. And so we may just go home and like slam the book and say, well, good, we've figured this out, Kim, right? We have like the models telling us this may happen, and we have the data telling us this may have already happened, and so we can call reporters and things like that. So this is the image we probably have in our mind of the data model into comparison I just took you through, and we should all feel really happy. But this is actually what is really at play, right, in most data model intercomparison things where you have to be careful. Very often you are not comparing apples and apples, and the more that you can understand that and really bring some rigor to that, the more information you can get about the system that may be critically important in helping us understand. So this is where we have to really talk explicitly about these isotopes, right? All of these proxies I talked to you about are really driven in part by this hydrological response, and most of them are really about changes in the isotopic pattern of variability across the tropical Pacific. Something we know very little, if anything, about. So that's a pretty strong caveat right there. I told you it's kind of like salinity. That is something that is really just a first order pass. And this is why we really need to understand this better, and this is why it's hard. So here I talked to the choral equation here. If you unpack this in terms of what we're actually looking at here, we have climate doing things, causing variability through space and time. That's manifest in changes in rainfall, oxygen isotopes. It's manifest in changes in ocean circulation, which together are compound into some kind of mixed layer change in seawater oxygen isotopes. Okay, this is something that is quite complex and involves a lot of different parameters of our coupled system. And we could really go crazy trying to bring data here because we really have no data here. We have very, very, very few seawater oxygen isotope observations to even begin to look at this. And so when you go into an environment like the Central Pacific, where you have very strong gradients, and you have very strong patterns of rainfall that are varying with circulation in complex ways, it's not very simple to unpack this. And so what we're looking at here is a working group that US CLIVAR just formed for the next 3 years, which is, I'm really happy to be co-chairing this with David Noon. And Adriana Bailey is on that. Where's Adriana? Is she here? Yay, there she is. She's also on this. Thank you so much for holding down the NCAR side of this. And so really what it's focused on is constraining the role for our water isotope observations and modeling in the climate system. And the idea is that this is really the essential glue, in a way, between the models and the paleoclimate data, and between some of the diagnostics that folks in this room may really care about regarding the cycling of water in the modern world and in the model world, and how we could bring these to bear. And so this is just a vastly untapped reservoir. The cool thing is we have new technology, benchtop, cheap, things that could go on airplanes, things that could go on ice cores. We have this really great laser system that enables us to make these measurements really, really quick and cheap relative to what we could do 20 years ago. And that's why it's really revolutionized this field. But we're kind of like stumbling forward in a very poorly coordinated and poorly thought out process. This is the time to start being strategic and to start realizing the potential of this tool. And so the key goal is to really think about incorporating water isotopes as an essential ocean and or climate variable. That's a steep climb because people worry about those lists, and what people have to measure on ships is a finite thing. But we really like to be part of those conversations. We'd like to think about what would a 21st century observational network look like. Willie Dansgaard designed the current network for rainfall isotopes back in the 60s, okay, as like what if we had a rainfall network? Wouldn't that be cool? Let's put some stations in. Let's start with Vienna, because it's in my backyard, right? And that's what we're still dealing with today. There's actually no strategic purpose to any of the current observational network that we have, other than grandfathered in from the 1960s. So we clearly have some work to do with that. We obviously need to leverage our technological capabilities as well, and not just rely on somebody's bottle parked in Vienna to collect some rainwater. We've come a long way. It's time to realize that. Obviously, as we amass all these measurements, we don't have a data archive. Nobody will take my data of water isotopes, right? GNIP says, oh, we only do biweekly samples from our network, right? IEA, I won't take it. So I have whole data sets like rotting on my personal computer right now, because I can't archive them with the ocean people, and I can't archive them with the atmospheric people, and I can't archive them with the ostensible isotope people, because their data set was designed in the 1960s. So we need a working archive that's the machine readable for modelers, that's actually standardized, and really applicable to the broad range of uses that we know are out there for these kinds of data sets. It's absolutely criminal what's going on right now. So we have to fix that as a working group, or at least get a map together. And then, of course, we'd like to look forward and think about what coordinated series of modeling experiments do we need to leverage these isotope observations and to unlock this potential in the isotope space. So I'm very, very excited about that, obviously. And I know all the people on this list are equally excited with this. And I want to note that there's a stunning lack of diversity on this list. We really tried our best to get some men to volunteer for this working group. We're going to try to do better next time. That's really all I can say about that. So I want to talk about some of my undergraduate work, because undergraduates are awesome. And this is a woman who did some incredible work in my lab over the last 4 years. Now she's a student at UW doing incredible work for somebody else. We're trying to get this paper done. Gemma O'Connor went with me out in the field and generated this incredible ensemble of auction isotope records spanning the 2015-2016 event, for which she has 8 different corals in play over that time period. This is the richest coral ensemble of El Nino events I've ever seen. I'm very proud of it. And you can see that the power in generating these kind of ensembles, I don't need to talk to this community about the power of ensembles, but in my paleoclimate community, this is a hard-fought battle. And so we can see that you can't just trust one coral for a 1997-1998 event, just like you can't trust one coral for a 2015-2016 event. But when you have more witnesses, you get a better story, and you can start to quantify your uncertainties. And this is the kind of work that we're trying to really push forward in our lab. And so when we line these events up, so you can play this game back to 1982, here's the 1997, 98, 2015, 2016 from Gemma's paper, and here are the various SST products, be they satellite or tau, or in some cases in situ from our lab. And you can see that while the SST kind of looks pretty flat here, the corals obviously indicating that the 2015-2016 event was larger than the 82, 83 event, 97, 98 event at our site. And so what we're able to do is go in and look at, we have discrete observations of water isotopes across the 97 event, because I was there personally as a graduate student on that cruise, and so I personally sampled those seawaters. Super great when your work could come full circle like that. And then obviously we have a lot of water observations from the 2015-2016 event, because we were down there every 3 months getting those samples as well. And so we could start to parse out the relative contributions of sea surface temperature and hydrology in these records. And so even for the 82-83 event, we almost have no hydrological signal. This was a famous case where the convective shift kind of just like skipped way over the Central Pacific and left us with only SST, actually, for the 1982-83 event. And you can see that visually in this kind of comparison. 97-98 event, a little bit more hydrological signal there from our data. And the 2015-2016 event, quite a significant contribution, up to 20% of that anomaly caused by Delta 18 in seawater, okay, that we could measure.
Northern Line Island.
Yeah, Northern Line Island.
Yeah. 'Cause I was there. 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 'Cause I was there.
Well, we don't have these kinds of records from the Galapagos. And in fact, the Galapagos have been a thorny issue in ENSO reconstruction because they warm by 6 or 7 degrees in a big event like 97, 98, and it just kills all the corals. So sometimes you have these, or they bleach and they stop accreting during those warm periods. And so you have these gaps in the very signal, right when you're interested in the magnitude of that signal, you're actually losing it in the coral archive. And so that's an issue in Galapagos that you don't have in the Line Islands, at least not until this last event. Now you have it even in the Line Islands in this last event. Okay. So yeah, ideally, Kevin, you could really play this game and go completely crazy over the tropical Pacific. But I need to stress how unique this kind of ensemble is for coral paleoclimatology. And so this, I'm not going to go into this data. This is just showing you some of the comparisons we're able to do. And so this was roughly 80% SST and 20% seawater delta 18 for the 2015-2016 event. So that's good. Now, I want to just flag the difference between roughly 20% seawater delta 18 contribution from the 2015-2016 event and the 30% change that I told you we saw from the pre-industrial era to the last 50 years of package of El Nino events, right? And so what that would mean at face value, unless we're quite wrong in some of our math, which is quite possible, and there's some uncertainties here, and so, but just at face value, this 20% seawater component is not enough to explain the shift from pre-industrial to today of ENSO properties. That would imply that there's a role for increase in SST variance baked into that signal as well as possible hydrological intensification, which is something we've already talked about. Okay, this is another one of my undergrads, super great. He's now a grad student in New Zealand. I miss him terribly. But he's been working on something very different and something I'm most excited about, which is extending this kind of piecemeal approach back through the 20th century. So these are corals that I picked up off the beach now that I'm adding into my calibration curve. They're uranium thorium dated, and they're run in the same way that our modern corals are. And so he's been adding all of these into our calibration interval, which is very exciting, and then extending this approach of these discrete little windows, if you will, back through the 20th century. And there's actually some hope, which is what I have hopefully a PhD student coming to work on, that we could actually create a continuous reconstruction. So here's the end of the modern coral record at Christmas, right here. We will never get another modern coral record from Christmas Island. First of all, they all died. Second of all, they were never that big to begin with, so they never would have penetrated through to the early 20th century. But this gives us a way, and I think the greater community a way, to piece together a continuous record that potentially could stretch back 200 years at the site. And it would be well replicated by its own construction methodology in terms of layering up these multiple realizations from these short snippets into a coherent ensemble. So here is what we have overlaying, I think this is ERSST, if I'm not mistaken, on the coral data that we have from the island. And again, I think that there's a lot of potential in milking this back through the last 200 years to generate the kinds of records that we could only dream of 5 years ago. And this is work from Sam Stevenson's. So when you go to play with these kinds of reconstructions in isotope space, it's best if you play with models that are outputting isotopes as well. And so when we try to piece out this hydrological component, whether it's with respect to the interannual frequency or the climate change signal or decadal variability over the 20th century, for example, we're really turning to models like this to understand how our sites, these are my 3 little dots in the middle of the Pacific here, how they may be, these are all output in delta 18 of seawater space on the top and salinity on the bottom here. Oh, no, temperature, delta 18 is seawater and salinity. And so you can actually see how different, for example, expressions of El Nino events, Eastern Pacific event versus Central Pacific event, impact the properties of seawater delta 18 at your site. And this is using a isotoped equipped version of the regional ocean model system that Sam has been working up as part of her initially postdoc work and now, of course, continuing in her faculty role. Very exciting tool, not well honed and perfectly accurate, not doing everything we'd like it to do the way we'd like it to do, but really forward-looking in terms of helping us understand some of these coral signals that are baked into the 20th century trends. And for the younger people in the room, I think this is really where it's at. We're in the business now as a community of trying to integrate these kinds of high-resolution paleoclimate archives with dynamical models that are isotope equipped in a kind of a data assimilation framework. This is an early such attempt led by Greg Hickam and Juliana Milget in the LMR, Last Millennium Reanalysis Framework. And so I can point you to Greg's paper where you can go through all of their results, the initial results, and they have kind of version 2 underway that takes off the isotope challenge as well, which they didn't in their first round. So it's exciting. I think it's a way for us to extend the instrumental record with these kinds of data sets. And so turning to, this is the Last Millennium Reanalysis. Also for the younger people in the room, there's an opportunity to get involved with the data assimilation project over the last century, the 20th century. And this is where I think the biggest gravy actually lies, of course. We have very few constraints on the mean state of the tropical Pacific basin as a whole in the early 20th century. So we may know there was an El Nino event. We certainly don't know what the rainfall patterns, what the salinity signatures were, even what some of the temperature structure was of the basin during that time. And so this is great because this is going to basically target explicitly a 20th century reanalysis that uses heavily corals in terms of understanding some of these thorny issues around force and natural variability over this, even in this time period, especially focused on potential hydrological impacts involved with salinity signals and rainfall proxies over the 20th century. Very exciting work. This is really what we need to be looking towards as a community. So just to summarize, I showed you our paleoclimate data now, which if we kind of bring the most burning question to bear on that expanded data set, we are able to identify a 30% strengthening in ENSO coming from the pre-industrial to the last 50 years. And this supports either increased SST variance in the Central Pacific and or a larger ENSO-related precipitation variance response in this region under climate change scenarios. And I would like to make a strong play for water isotopes as the key for unlocking the potential between these kind of paleoclimate records I showed you today and some of those burning questions in climate science involving trends and extremes and dynamics that we would all like to know more about. And so you can join our working group if you're interested in signing up. We're just getting underway. We're just setting our agenda for the next 3 years, and we'd love to have you join us at our meetings and think about what you would bring in terms of passion and purpose to the table. It's a come one, come all. And I wanted to end on this kind of more personal note about what happened to my research site over the last major ocean temperature heat extreme for El Nino, and this is a 2014 shot of the same site that you can see on the right here, kind of before and after this El Nino event swept through. And so it killed 85% of the reef that I've been working on for 20 years now. And of course, the recovery will take decades in itself, like a vast scientific treasure trove of information about resilience and lessons and ways that we could help in this natural laboratory setting. But this is why I would point you to the talk I gave yesterday as kind of a leaping off point for motivating a whole different role for myself as a scientist in the public discourse around climate change, especially as we find ourselves in an era where climate science and climate scientists and facts around our science are under such withering attack. So please check out those slides or ask me for them if you're interested. I'm happy to take questions on that space for people who may not have been down there, but I may have watched it and wanted to ask a couple questions as well. So thank you so much for your time.